are in listen-only mode.
Hello everyone and welcome to the webinar. This is Sydney speaking, and as you all know, today's webinar is based on HSM. What we're going to do is very similar to what I've done in my previous last two webinars. Is I'm going to take apart, started from the very beginning, and when I start working on HSM, one of the things I like to point out in HSM is that people look at a part such as the one I have on the screen and they say to themselves they have to do this part with one, they have to do the finish HSM operation with one entire type of technology over the entire part, which I'd like to actually show that many times, such as a case like this should be actually broken up into different types of operations. And you'll see what I'm talking about in a few minutes. Now, as usual with every webinar, you'll be allowed to ask questions. If you have any questions, all you have to do is in the area where you have your raise hand, click on raise hand, and in the question box, write down your question. And when you finish writing down the question, don't forget to click on the send button. This way I can answer the questions, because then I'll be able to see the questions as well. Okay, so let's get on to the webinar itself. Now, as you see, I have this screen on the screen. As you see on the screen, I have this part that I want to machine. This part is actually a pretty large part. It's approximately 600 millimeters by 500 millimeters. And it's pretty complex also. It has parts that's actually core on top over here. You have actually pocketed area, cavity areas over there. You have all different types of areas on this particular part itself. And as I said, it's also a pretty large part as well. Now, this is the part I have my stock predefined over here. You can see I have it as a configuration. That's going to be my stock over there. And I also will be using a fixture that looks something like this. This is going to be my fixture. Okay, so let's start my operation itself. First, I'll start my SolidCAM project by going into SolidCAM new milling, checking that this is the right part that I have, HSM part, same part that I have over here on my screen. Everything's set. This is where it's going to be saved, the part. And we'll define our home. Our coordinate system, I want to have it in this particular case exactly in the middle of the part. So I'll click on this face over here. And we have it exactly in the middle. However, what I'd like to do is, as you can see, the x-axis is going along this face over here. And I'd actually like to have this face facing us instead. So what I'm going to do is, when I have my home is exactly like this, I just want to flip it around my Z by 90 degrees so that the X is in this direction. So all I do is click flip on around Z, and you can see the home position moved. I'll just accept that. And as you can see, the part flipped to the exact direction I want to have it in. Okay, we'll continue on down. And all I want is one home position for now. And let me go define my stock. If I define my stock, now since I have a stock already defined as a 3D model inside my configurations, so I'll do defined by 3D model and choose my configuration, in this particular case my stock configuration, and click on my stock over there. That's my actual stock. Showing it over here, you can see that's the stock that we're going to be using. Okay, we're all set with that. My target is already pre-picked for me. That's because I have it in my settings to pre-pick my target for me, so I don't have to go and choose my target. Now, I'll accept it exactly the way it is. Now, before I continue on, I just mentioned a couple seconds ago that my target was automatically there. This is because if I go into my SolidCAM settings over here, you can see that when we have automatic cam part definition, you'll note I have checked off definition of target. That's done automatically. Definition of stock is not done automatically, but my target, that's what I want automatic. Okay, and this actually saves me the time of having to pick my target itself. Okay, now next thing I'd like to do is bring in my fixture. So we'll go into my assembly and insert component. Since my fixture is already open, it appears on my list over here. And I'll just bring it in over here for now. Next, of course, I need to mate it. So we'll do our mating. We'll have this surface of the fixture up until this surface of the stock itself. Note I'm mating it to the stock. We'll have this surface and this surface over here also coincident. And now what I'd like to do is have this exactly in the middle of the part. So for that, since the way I like working is having always a surface, working plane always in the middle of my part and in the middle of my fixtures, it makes it a lot easier to do my mating that way. So I'll go into my design model and I'll choose, here I have my front plane in this particular case is right in the middle of the part. I'll choose that. And if I go into my fixture, I also have one of my faces, one of my planes in the proper position. My right plane is exactly what I'm looking for over here. I'll just click on it and you can see both of them are now coincident one to another, making sure that this part is now sitting exactly center of my fixture. Okay, so I'm set with as far as bringing in my fixture. One other thing I'd like to do is, since I mated my fixture to my stock, I like to put my fixture also in the same configuration as my stock. So this way, when I have my stock disappear, my fixture is not sitting on nothing, thereby giving me some kind of an error. So I'll just go into my tree, my assembly tree, and right-click on fixture, and we'll go into configure component of the fixture itself. In the configure component, I'm just going to tell it that when I choose my default, I want that to be suppressed. And if I go into my configurations, you can see now if I double click on default, my stock is gone and so is my fixture. Going back over here, we're all set. Okay. The last thing I like to do with the fixture before I actually start working on the part itself is just setting it up, defining my fixture, and also setting it up for the machine simulation as well. I'll right click on operation and go to machine setup. In machine setup, I'll just go into fixture. Since I didn't define my fixture yet, I'll just click over here and choose the option over here to define. By clicking over here, all I have to do is click on the fixture itself. If I click on show, you can see the fixture itself was chosen, and I'll click on OK. Now we have the fixture inside my settings. All I have to do now is just set my Z level. My X and Y is exactly in the middle, so I don't have to change that. My Z, I'll just right click over here, pick Z, pick out one of the bottom elements of my fixture itself. And we're all set as far as that goes. Okay, now we're set to start machining the part. Now, the first operation I'd like to do is a roughing operation in HSM, which is actually HSR. HSR is the roughing of HSM. So we'll start with 3D HSR. And I'm going to use the option of HM roughing. The tool that I'm going to use, well, let's go into my tool list. Now, you'll note when I open my tool list, I have all of these tools over here. This is part of my machine tool list that came in once I defined my part with this particular machine. And you know what? In this particular part, I'm not going to do any kind of drilling operation right now or anything else like that. The only thing I would like to see here are just regular end mills, ball nose tools, and bull nose tools as well. So what I'm going to do is very simple. I want to erase all the tools that are not of those types. What I'll do is simple. I'll just click over here. I'll clear the entire list and actually choose only the tools that I don't want to use. I'll choose these tools here, leaving the end mill in, ball nose, and bull nose. Those are the tools I'd like to work with. These are the tools I don't want to work with. So I'll click on OK. And now that I see all those tools, I'm just going to select all of them and delete them. Because those tools I will not be using in this at all. So all I want to do right now, if I take away my filter, these are the tools that I want to be able to see. Actually, I don't see all of them. There are some of them that I forgot to take. For instance, the tap one, no problem. I'll just do a tap, thread, and I'll delete those as well. Apparently I missed those, so I'll just do it right now. Okay, so this is the list of tools that I have. And as I said, I want to start with a very large tool. The reason for that, because this is actually, as I said in the very beginning, a very large part. So we'll click on, we'll click on the large tool that I have here, the 30 millimeter end mill. And it has to go also pretty deep. So it's actually a pretty deep tool, sticking out pretty much a nice amount out of the holder itself. And I'll select that tool. My constraint boundaries, I'll do it automatically according to my target. The reason why I'm not making any changes over here is very simple. The outside dimensions of my stock is the exact same as my part itself. So it really doesn't make a difference if I choose stock or target as far as the outside boundary, because they're both the exact same. Okay, we'll go into passes. Now, as far as my wall offset goes, I'm going to leave at this point 0.3 millimeters of excess material on the wall and floor. And my step down, being that this is a large tool and I want to take out now just a large amount of material, I'm going to go down every 5 millimeters. Now, my Z depth, let me just actually change this so it makes it a little easier to work. My Z depth is going to be up until this step over here. I don't have to go any further down than that because everything on the outside over there is already the exact same measurements that I have from the outside of the part itself. The stock and is the exact same thing over here. Okay, one more thing in my constraint boundaries. I'd like to change my boundary tool relations to be external, to make sure the tool can actually go from the outside of that stock. We have our passes, as I said, and we have two options over here. We have actually three options. We have our core, cavity, or H spiral. Now let's take a look at the part itself before I decide what I want over here. The part itself, it looks like we have actually a core over here, a flat surface with a nice core over here. In essence, really, we also have, it's not a full core over here, we actually have also pockets over here. Now, what would happen if I would choose the option of core? Well, let's run our calculation. The calculation will take a couple moments because it has to, like I said, it is a large part. So the calculation is going on right now as it's calculating every step down. And again, because it is a large part, so the calculation does take a little longer. Now, normally if I would be working and I know exactly what I'm doing already, I wouldn't be doing a regular calculation. I do calculate and save, external calculate, and go to my next part. This way I don't have to wait for this to finish. But since I'm actually showing you everything, so I want you to see every single step of the point, so I'm just waiting until this finishes. Otherwise, I could have clicked on this over here, and that would have put me into the next operation. Okay, let's run our simulation, and note what's happening when I run my simulation. I'm going to do it kind of slow, and you'll note that it's working from the outside in at all points. When it gets to this surface over there, it's actually jumping up, always trying to go away from it, trying to avoid those areas. All right, it's not a problem. It'll actually work, but it's not the most efficient tool path in this particular case. Okay, this is not a pure core part. There's some parts that are actually pocketed in there also as well. So this is giving it a little bit of confusion. But however, it is doing the work, and it's doing it actually pretty well. But let's see a different option we can use instead. Let me actually stop this. And we're going to use the option of, instead of core, we're going to use the option of HSM. HM spiral. When I choose the option of HM spiral, it'll actually work in a spiral manner around the part itself, taking on the shape that's sort of in the middle. It'll actually clean the corners first and then start working around, and it'll actually be a more efficient tool pass. Now, you can work in either way, but you have to decide yourself which is more efficient for your particular case. They both give you the same result, but as far as the efficiency of the cut, in this particular case, HM spiral is better. And we'll see that in a few moments, the moment the calculation is done. We'll take a look at the top view of the simulation, and you'll see that it's first clearing off the corners as shown over there, this one over here as well, and now after it finishes the last corner, it's actually working spiral around, going into the part itself. Note it's taking the shape of what's over here, of what actually has to be cut out over there, and then it's going to go all the way around over there as well. Now let's stop over here and run this using Solid Verify simulation so we can actually see this on the actual stock, what's going on. As you can see now, there we go, sorry. There we go. Its part is being cut from the outside in. You can see it taking the shape as it's going in as well. And we're getting actually a very efficient tool pass going into the part itself. Now, like I said, we have large down steps. We have down steps of every 5 millimeters. I have no problem with that. Remember, this is a large part. And I first want to take care of the bulk of the material as quickly as I can. So I have a large end mill, and I can take those big steps. But then afterwards, obviously, I have to do what they call a rest roughing operation. Note it's clearing off this step here as well as the other side. You'll also note one other thing. There were holes over here, these large holes which were 50 millimeters in diameter. The tool did not go in there. The reason for the tool not going in there is very simple. And actually, I don't want the tool to go in there. The reason why the tool did not go in there is very simple. If I go into my link, let's first look at the tool. The tool itself is 30 millimeters in diameter. If I go into my link, you can see that my minimum profile diameter is set at 33. So if I take 33 and 30, that makes 63. 63 is larger than the hole itself, which is 50. Therefore, there's no room for it to move in over there. Let's just take a quick look at this diagram I have over here. If we have the tool diameter, we have the diameter of the hole, the tool diameter, this is the minimum profile diameter. If this overlaps with the tool, then the tool will not go in. This is exactly what happened in this case. Therefore, it prevented the tool from going in. Okay, now for my next operation, I'd like to do another roughing operation, but this time we're going to do a rest roughing operation. So if I go into rest roughing, I'm going to choose a smaller end mill. In this particular case, I'm going to choose an end mill that is a bullnose of 20 millimeters, 20 millimeter bullnose with a 2 millimeter radius. That means the bottom of the tool, it has a diameter of 16 millimeters. Remember that value, and you'll see why in a couple of moments. I'll do select. My constraint boundary is exactly the way it was in the previous operation. In my passes, this time, my step down is going to be every 2 millimeters. Okay, now I'm not working on the entire part. I'm just working on the areas where the previous end mill could not work over there. Now, one other thing is that my Z bottom, I want to change that. I don't want to go all the way now down to the bottom over here. First of all, there's no reason for me to go all the way down over there. So I'm just going to limit it to go up until maximum that surface over there. This looks fine to me. Let's run our calculation for a moment. And the first thing it's doing, it's calculating what's the material, what's the rest material that's left over from the previous operation. And like I said, the part is a relatively large part, so it's taking a couple of moments. But as you see now, we're getting to the actual calculation of the tool pass itself. And as we're finishing down over here, we're just finishing off that surface, calculating those passes over there. Okay, we're almost done now. Okay, let's take a look at the simulation. We'll do this in wireframe the way it is now. It's working in these areas, only in those areas. And note that it goes down over here, but also note that it went into the holes. And let me stop this now. Okay? It went into the holes, and I don't want it to go into the holes. So what I'm going to do is, in order to prevent it to go into the holes, remember I mentioned that the minimum diameter at the very bottom of the tool is 16 millimeters? Well, let's go into our link. Our hole itself that we have over here, like I said, is a total of 50 millimeters. So if we take 50, subtract 16 from that, that will give us 34. So the minimum profile diameter has to be at least 34. And that's why I'm putting it that. If it's less than that, then the tool will go in as you've seen it go in. So now all I did was, instead of creating a boundary around it so I don't have to go into it, all I do is just change my minimum profile diameter in this case, run my calculation again. Since the stock was already calculated for this part and no change was made in that previous operation, so that the stock does not have to recalculate itself. It's just going directly into calculating its tool path. And as you can see, in a moment we'll be finishing our calculation. And I want you to note what happens when we run our when we run our simulation over this area over here. You'll note that the tool is working on the outside areas as shown over here. It's working on whatever's left over on this surface over here. But note, it did not go into the holes this time. I prevented it from going into the holes just by changing the minimum profile diameter. Now I want to do one more roughing operation, because still leaving 2 millimeters of a downstep on those edges, it's still a little bit too much for a finishing operation. Plus there are also areas where this tool was not able to go into. So I'll just do save and copy, keep the rest roughing, just change my tool now to a 12 millimeter bull nose with a 1 millimeter radius, giving it a 10 millimeters at the very bottom of the tool itself. In my passes, I'm going to step down now every 1 millimeter. And in my links, I'm going to change this to 50 minus 10, which is 40 millimeter diameter. Calculate it. Now it's calculating the previous stock from the previous operation. And then it will go into calculating the actual tool pass itself. As you see, that's what's happening in a moment now. It's calculating its rough passes. Remember now, I did a smaller step down, but it's a much smaller area that it has to work in. You'll see that in a moment. We're almost finished with the calculation over here. And now you'll note, again, it will not go into those holes. And it'll only work in specific areas where there's actual material left over and where you have and where it can actually minimize those steps to 1 millimeter instead of 2 millimeters. Okay, we're just about done over here. As the calculation is going on, we're getting now close to the end. Now let's take a look at the simulation. And again, you'll note it's only working in areas where it needs to work. The rest of the areas is not being touched at all. Okay, and again, it did not go into those holes. Okay, now we're ready to start some of our finishing operations. Now, again, what I'd like to show you, especially now with the HSM and the finishing operations, is that you do not have to finish everything off with one type of technology. In fact, I like to break it up into different areas. Now, the first thing I like to do, the simplest thing, is just do what we call a horizontal finishing for the floors itself. Now, we have a floor over here, and we also have floors down here as well as over here. Well, in this particular operation, I want to first start off with this floor over here. Now, the reason why I am not doing this floor together with this floor in the same operation is because I need a really long end mill to get down over here. Plus, I have to clear away this wall to get down to that surface. So I'm going to save that for a different operation with a different type of tool. You'll see what I mean in a moment. If I go into 3D HSM, I'm going to use the option of horizontal machining. My tool in this particular case is going to be a 16 millimeter end mill as shown over here. My constraint boundaries, I'm going to leave it exactly the way it is, not making any changes. And in my passes, I'm going to limit my step down to this surface over there. That's the most I'll go down. Now, let me run my calculation. Now, since it's a horizontal machining, it works only on the flat floors. Flat floors, I mean flat floors that are 0 degrees, exactly horizontal to the part itself. If I take a look at the simulation, you'll note that the tool works on those surfaces. But note one thing, something I didn't really like too much over here. You'll note that when it entered the part, it actually went down onto the part, a helical into the part itself, which is fine, but really not the most nicest type of tool path I'd like to have. I'd actually like to go from the outside in. So for that, inside this option over here, we also have detect core areas. Inside our passes, we have also detect core areas where it'll actually look to areas to work in from the outside in. Again, let me run my calculation. And as you see, we have the calculation going on. It's calculating the horizontal areas, and it'll finish that in a moment. Now, again, remember, this is a very large part itself. So the calculation on this actually does take a longer, but for a large part, it's not going that slow at all. Note, in this particular case now, the tool is actually entering from the outside of the part itself. As you can see, it started from the outside. There's no helicaling onto the surface itself. Okay, now next I like to continue on down to this surface over here. But I also have to machine these walls as well. So what I'm going to do is I'm going to do save and copy to start a new operation, And instead of horizontal machining, I'm going to use combined constant Z with horizontal machining. The constant Z will work on these walls, and the horizontal will work on those floors. Now, my tool in this particular case must be a longer end mill because this cannot touch this surface over there. So we need it to be a longer end mill, and I happen to have one ready for me. I have a 16 millimeter end mill sticking out the amount that needs to stick out of its holder itself. The constraint boundaries, I'm going to change that. I don't want the whole part now. I only want these areas over here. So what I'll do is I'll do create manually, use a defined boundary, and I'll go into multi-change, clicking at that surface over there, and accepting it. So I have my two chains over there, and I'm just going to make sure I'm going in the center of those areas to making sure it gets to the very edge and also over the edge of that surface over there itself. My constant Z passes, my Z top will be over here. My Z bottom will be over there. My step down will be every 6 millimeters or even every 8 millimeters. And one more thing, if I go into my link area, I'll be working climb milling. In other words, I won't be going bi-directional. I'm going in one direction only, and that will be climb milling. And I'd like to actually lead in with an arc. So if I go into my leads, the way it normally goes in, it actually helicals its way down onto the edge over there. I'd like to do what we call a basic horizontal approach, where if I have my lead in, you note, it'll actually go in with an arc, starting with an angle of 90 degrees into the part itself. The same thing with my lead out. And the radius that it's going to be using is actually put in over there. You can actually see, according to the diagram, what's going to happen. Okay, that's as far as my constant Z passes. My horizontal passes, I'm just going to set my upper level being over here, this surface over here, and my depth being, my Z bottom being that surface over there. We'll run our calculation. Remember, now it's doing both the calculation for the constant Z passes, which is going to be every 8 millimeters, and my horizontal floor machining as well. Let's take a look at the simulation. You'll see we have our let's do it a little slower. Okay, we see we have our passes on the outside going in one direction all the time. We have our lead in and lead out as shown over here on each level, and then when it finishes, it does the very bottom surface over there as well. Okay, so as far as this part goes, we have all the flat areas taken care of. Okay. Now, next I'd like to start working on this area over here. The area that's a little more complicated. Now, the way I'm going to do it is, let's first start out by trying to take the entire area and finishing that off. What I'm actually going to do really is I'm going to go into 3D HSM, but instead of taking the entire area and finishing it, I'm going to take the entire area and give it a semi-finish. Semi-finish, in especially when working with molds, is very actually customary to do it that way. This way, giving it for a smoother finish as for your finished cut itself. Okay, so we'll do instead we'll use the option of 3D constant step over. Now, in 3D constant step over, first I'm going to use a ball end mill. The ball end mill that I'm going to use is going to be a 10 millimeter ball end mill. Now, one thing I always like to do when I'm working with finish cuts, especially in areas where I see the tool is going to go into this area over here, or in these areas over here, and it's going to have actually, it's going to have areas where we have sharp turns in there. So I'm going to go into my geometry and do an applied fillet. And I'm going to give it an applied fillet that's larger than the tool itself, thereby automatically creating a fillet in those areas so that the tool doesn't make any sharp kind of turns in those areas. Rather, it goes according to the fillet itself. Next, we have our tool as I chose it. My drive boundary, let's choose a drive boundary, a new one. And we're going to choose this edge over there, going around this entire area over there. That's my drive boundary, and my constraint boundary will be the exact same. Constraint boundaries will be the exact same as my drive boundaries, so I'll choose that. And my drive boundaries, I'll have that set at, we'll leave it at centered the way it is right now. Excuse me. And my constraint boundaries, I'll have that the same way. Let's go to my passes now. In my passes, we have every 1 millimeter, and I have my wall and floor offset. Now, let's set my wall and floor offset at 0.2 millimeters, since this is a semi-finish operation. So I want to leave a little bit of material for the finish. And my horizontal step over, normally I would leave it at 1 millimeter, but since I want my calculation to go a little quicker over here to save time for the webinar itself, so I'll have it every 2 millimeters. Now, note what's going to happen. We have our tool, and in our tool itself, let me just open it up again. The tool itself, it's outside the holder by 60 millimeters. Well, we have something here called holder clearance. This prevents the holder from actually hitting any material if it gets too close to the part itself. Now, I happen to know that this area over here is larger than 60 millimeters. In fact, it's 70 millimeters. So the tool will not be able to go all the way down over there. So I actually need a tool that's sticking out more than this tool itself. So I'll just lengthen this tool a bit by making this a 120 millimeter end mill. Outside the holder, I'll give it a total of 100 millimeters. And now we're all set over there. Now let's run our calculation. And what's going to happen is the tool will actually work its way in the part. Now, one thing I didn't do, and actually let me stop it for a moment. The way the tool pass is going to work from the inside out. I'd rather work from the outside in. If I go into my link area, all I have to do for that is to go from first pass, going from the outside in. Now let's run our calculation. And remember, I do have filleted surfaces over there. This way, well, I won't have any kind of a sharp edge over there, or sharp turn into the surface over there. Okay, right. So it's calculating. First, the thing it does is calculates its fillets. Now it's calculating its actual 3D constant step over passes. After it calculated it actually build the fillets within the system itself. Excuse me. Okay. Again, remind everyone, this is a large part. This is why the calculation is taking a little longer. However, even for a large part, the calculation is going relatively quick. Because, by the way, HSM, if you didn't know, HSM uses multi-core for the calculation of the part itself. So the calculation is actually going quicker. However, like I said, it is a large part. So that's totally acceptable, the amount of time it's going for the calculation over here. Okay, it's almost done. Now it's doing the calculating the step over. Before it was a step down, a step over, and now it's just generating its toolpath preview. Let's take a look at the actual toolpath that we have over here. You'll see. Let me go a little quicker over here. It's going around the part exactly the way I wanted it to go around. Now, it didn't go to the outside over there. That's because I'm not going to recalculate it now. That's because I should have been external instead of centered. But you can see we can get that nice toolpath that I needed over there. To take care of that area over there, in my dry boundaries, instead of centered, I would have external. And as far as my constraint boundaries, the same thing would be over there. But let's continue now with the part itself. And this was the semi-finish. Now, before I go into my finishing operations, let me just explain one thing. I can do a finish operation using the exact same type of technology. Not a problem. However, when working on molds, and especially large part like this, where you have different areas with different types of shapes, there are many times you want to use different types of technologies for different types of surfaces. As you saw over here, I did the horizontal. Over here, I'm actually going to break this down into different type of technology. Okay, I don't want, for instance, this to have the exact same technology as the one as inside over there. So let's just see some of the different ways we can actually break this down. I'm not going to do too many of them, but let me just do some of them. I'll start my 3D HSM operation, and I'll choose the option of 3D corner offset. And what I'd like to do is choose my end mill. My end mill is going to be a 6mm ball end mill, which I have right over there. Being the 6mm end mill that I have over there, I'm going to go into my geometry and put in an applied fillet over here of 10mm. No problem at all. We have our tool. We've done that. My constraint boundaries. Now, my constraint boundaries, I'm going to use the option of selected faces. By selected faces, we're going to do the following. I'm going to select the faces I want to work on by clicking on this surface over here, this surface over there, this surface, and this surface. You can see those are the surfaces that I'm going to be working on. Now, what's actually going to happen is I want my tool to work according to the shape of those surfaces, which is exactly what's going to happen. Now, just to make sure my tool doesn't hit the edges over there, I'm just going to give it a little bit of an offset of 0.5mm, and then accept my faces that I selected, and now it's building the boundaries according to the information that I just gave it. This will take a moment as calculating the surfaces. If I do click on modify, you can actually see the boundaries that was built above the part itself, showing exactly where it's going to work on the part. Okay. I have my pencil passes. Now I have my passes itself. We have our horizontal step over, and I'm going to have this at every 2mm. The reason why I'm having it every 2mm is so that the calculation does go a little bit quicker. I'll run my simulation. After, of course, it calculates the part itself. As you can see, the calculation is being done. And again, by the way, if I didn't mention this before, this webinar is being recorded, and you'll be able to have it tomorrow. You'll be able to review it again on our website. This time, however, the part itself will not be available, as this part belongs to a specific customer who said I can use the part, but I cannot give the part out at all. So the part has to stay with me, but you can see the webinar. You can actually understand exactly what's going on over here. Okay, the calculation will be done in a few moments. As it's calculating first, the edges according to the shape that I want to work on. Okay, we're now it's calculating its passes. Let's take a look at the actual simulation. Just a moment, please. All right, I want to see what happened over here. Sorry, the calculation didn't work correctly. Let's do it now. I accidentally stopped the calculation, so I'll just restart the calculation. Okay, that's what happens when you work too quickly. I accidentally touched the cancel calculation button, so we just redo it over there. Okay, like I said, it's calculating those fillets that I first built in. And after it builds those fillets, and it can then continue calculating in the rest of the tool pass. As it has to calculate the fillets into its boundaries as well, as far as the surfaces that it has to work on. Okay, let's finish the calculation. Okay, for some reason the calculation had stopped. Okay, one moment, please. I think I know what the problem is. Okay, just one more moment. Okay, let's run this simulation now. And as you can see now, it's working exactly on those surfaces over here, as shown over here. Okay, note it also took the exact shape of those surfaces. Now, I still want to work in this area over there. So for that, I'm going to use a different type of technology. I'm going to use the exact same tool, but this time I'm going to change it to 3D constant step over. Use the same tool. My drive boundaries, this time I'm going to use not selected faces, but a user drive boundaries, and my boundary itself will be this circle over there. We'll accept it. I'll keep it centered. My constraint boundaries will be the exact same boundary as I have now. As you see, contour 3, contour 3. Passes, we'll have that set at every 2 millimeters. And this time we're going to be going from the inside out. So I'm going to leave the from first pass alone, leaving it from the inside out. Running my calculation. my simulation. As you can see, it's working inside over here and taking on the shape of this area. Note, even when it worked on this steep wall over here, we had the exact same constant step over as we did on the floor itself. So we had one type of technology over here and another type of technology over here. Now I can continue on and on and on with this part. The idea behind this part to show you was very simple, is that I do not have to use only one type of technology to finish off the part itself. I can, instead of doing what people tend to do, is they tend to take this entire area and do the whole thing with 3D constant step over, which is not necessarily the best way. The best way, and actually as I showed you over here, was actually breaking it down using different types of technology. So what the idea is to learn all the different types of technology that we have inside HSM itself, and find for each area, just to break it down and do different operations for each particular area itself. Okay, I'd like to thank everyone for joining us in the webinar itself, and everyone should have a great weekend. And as I said, the webinar will be available on our website. Take care, everyone.